sketch the graph of the function f of x equals 2x to the 5/3 minus 10x to the 2/3 by determining the parts a through I. F of x equals 2x to the 5/3 minus 10x to the 2/3, two terms that are fractional exponents. The denominators of the fractional exponents are the roots. They're each an odd number here. And the domain of an odd root is all real numbers. So for part A, the domain will be all real numbers, or negative infinity to positive infinity. For part B, we want to determine if there is any symmetry. This is done by evaluating f of negative x and comparing it to the original function f of x. F of x is made up of two terms of fractional exponents. The first one has an odd root, the denominator, and an odd power, the numerator, so it will have origin or odd symmetry. The second one has an odd root, the denominator, and an even power, the numerator, so it will have y-axis or even symmetry. Since the two terms do not match each other, overall f of x will not have any symmetry. F of negative x is 2 times negative x to the 5/3 power minus 10 times negative x to the 2/3 power. For the first term, negative to the 5/3 means cubed root of negative, which is negative to the 5th power, which is still negative, and that negative can move out with the 2 to be negative 2, and then the x to the 5/3 power. For the second term, the negative to the 2/3 power, cubed root of negative is negative, to the power of 2 squared will be positive. And then times the negative 10 will be negative 10, and x will still be to the 2/3 power. Comparing the first term to the original, it is the opposite sign. And therefore, f of negative x does not equal the original function f of x, and so it will not have y-axis or even symmetry. Comparing the second term to the original, it has the same sign, so f of negative x also does not equal negative f of x, so it will not have origin or odd symmetry. So for symmetry, it has none. For part C, we will determine the y-intercept. This is the point where the graph crosses the y-axis, defined by x equals 0. We can find the corresponding y-coordinate by plugging the x-coordinate 0 back into the original function. Y equals f of 0, which is 2 times 0 to the 5/3 power minus 10 times 0 to the 2/3 power. 0 raised to any non-zero positive power is 0, so this will be 2 times 0 minus 10 times 0. 2 times 0 is 0, minus 10 times 0 is 0, 0 minus 0 is 0. We had an x-coordinate of 0, and we found a corresponding y-coordinate also of 0. So the origin is the y-intercept. For part D, we want to determine the x-intercepts. These are the points where the graph crosses the x-axis, defined by y equals 0. Y, which is f of x, is going to be set equal to 0, and we're going to solve for all x's. We will want the function to be fully factored for this. So back up here, we will factor the function. There is a common factor of a 2, and there is also a power of x, the lower of the two powers, which will be the 2/3. Can factor out. And that'll leave behind, factoring out the 2, this will become a 1, and this will become a negative 5. Factoring out an x to the 2/3, factoring is division, and division is subtraction of exponents, so we're going to subtract a 2/3 from each of the powers. 5/3 minus 2/3 will be 3/3, or 1. 2/3 minus 2/3 will be 0, and x to the 0 is a 1. So we have 1x to the 1, or just x, minus 5. X minus 5 is what's left after factoring. So y, which is f of x, will be set to be a 0, and it can be set equal to the factored version of the function. And since it's factored, we can easily solve. Because of the x to the 2/3, we get x equals 0, because 0 to any positive non-zero power is 0. And from the factor x minus 5, we get x equals 5. We have a y-coordinate of 0, and we found the corresponding x-coordinates of 0 and 5. So that'll be 0, 0, and 5, 0 as the two x-intercepts. For part E, we want to determine the vertical asymptotes. F of x is two terms that are fractional exponents. They are both positive powers. There is no denominator, so there will be none. For part F, we want to determine any wholes. F of x has no denominator, so there is none. For part G, we want to determine end behavior, horizontal asymptotes, or slant asymptotes. F of x is fractional exponents with no denominator, so there is no horizontal asymptotes or slant asymptotes. But because we have powers of x, it will have left end and right end behaviors of positive infinity or negative infinity. We can determine the left end behavior by taking the limit as x approaches negative infinity of the function 2x to the 5/3 minus 10x to the 2/3. Only the highest power term will matter here. Negative infinity to the 5/3, cubed root of negative infinity is negative infinity to the 5th power is still negative infinity times a 2 will be negative infinity. We can determine the right end behavior by taking the limit as x approaches positive infinity of the function 2x to the 5/3 minus 10x to the 2/3. Only the highest power term will matter here. Positive infinity to the 5/3, cubed root of positive infinity is positive infinity, to the 5th power is positive infinity, times 2 will be positive infinity. For part H, we want to determine the intervals of trend, relative maxima, relative minima, plateaus, and cliffs. All of this involves the first derivative, f prime of x. Taking it from f of x, each term is a power rule. First term, bring the power down, multiply with the 2. 2 times 5/3, multiplying the numerators. 2 times 5 is a 10. Over the denominator, 3. X raised to the 5/3 minus 1 minus 3/3. 5/3 minus 3/3. 5 minus 3 is a 2. Over 3. For the second term, bring down the power, negative 10 times 2/3. Multiplying the numerators, negative 10 times 2 is negative 20. Over the 3. And then subtracting 1 from the power, 2/3 minus 1, 2/3 minus 3/3. 2 minus 3, negative 1, 3rd power. We will want to fully factor the first derivative. There is a common factor in the numerator of a 10, and in the denominator of a 3. And then we can factor out the lower power of x, and that will be the negative 1/3 because it is negative and the other one's positive. Factoring out the 10 will make this be a 1 and this be a negative 2. Factoring out the 3 in the denominator will cancel these out. Factoring out the x to the negative 1/3 power. Factoring is division. Division is subtraction of exponents, so we'll be subtracting a negative 1/3, which is equivalent to adding a 1/3 to each power. For the first power, 2/3 plus 1/3 is 3/3, or 1. And so we will have left there 1x to the 1, or just x. For the second power, Negative 1/3 plus 1/3 is a power of 0, and x to the 0 is a 1, and we will have a minus 2. So we have 1x to the 1, or just x, minus 2. X minus 2 is what's left over after factoring. We want all powers to be positive, so we will move the x to the negative 1/3 to the denominator to become a positive 1/3. The 10 stays in the numerator. The x minus 2 stays in the numerator. There's a 3 in the denominator, and the x to the negative 1/3 will move to the denominator to become a positive 1/3 power. So we now have the first derivative written as a single fraction. All powers are positive. It is fully factored. We can set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. From the numerator, it's factored, so that will tell us that x equals 2. From the denominator, we have x to the 1/3 equaling 0, and that means x is 0 because 0 to any non-zero positive power is 0. We'll now check to see which of these are in the domain. The domain's all real numbers. X equals 2 is a real number. X equals 0 is a real number. They are both in the domain. They are both a critical number. We can now draw a domain line, a line representing the domain. It has no left end because it begins at negative infinity. It has no right end because it ends at positive infinity. We can put all critical numbers on here in order. X equals 0 comes before x equals 2. This splits the domain interval into 3 separate intervals. We can pick a test value in each of the intervals. The first interval, negative infinity to 0, we can pick negative 10. The second interval, 0 to 2, we can pick 1. The third interval, 2 to positive infinity, we can pick positive 10. We can test the trend by plugging the test values into the first derivative. We only care whether it is positive or negative. So we will plug into the fully factored version. That's this one here. Plugging in the negative 10 minus 2 is negative, times the 10 will be a negative, over negative 10 to the 1/3 cube root of negative 10, which will be a negative, times the 3 will be a negative. We have a negative over a negative, which is a positive first derivative, and this corresponds to an increasing trend. Plugging the 1 in to the fully factored version of the first derivative, 1 minus 2 is negative, times 10 is negative, over 1 to the 1/3 cube root of 1 is positive, times the 3 is positive. We have a negative over a positive, which is a negative first derivative, and this corresponds to a decreasing trend. Plugging the test value of 10 in to the fully factored version of the first derivative, 10 minus 2 is positive, times 10 is positive, over 10 to the 1/3 cube root of 10, which is positive, times 3 is positive. We have a positive over a positive. That is a positive first derivative, which corresponds to an increasing trend. Right at the critical number of x equals 0, we have the trend change from increasing to decreasing, which means x equals 0 is a relative maximum. Now over here, x equals 0 came from the denominator of the first derivative, so it is not a normal relative maximum. It will be a cusp relative maximum. So we have a cusp maximum occurring at an x-coordinate of 0 and a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of 0. It's best to plug into the factored version of the function, which is this one here. 2 times 0 to the 2/3 times 0 minus 5 will be 2 times 0 to the 2/3 will be 0, because 0 raised to any non-zero positive power is 0. 0 minus 5 is a negative 5. 2 times 0 times negative 5 will be 0. So we have a corresponding y-coordinate of 0. So we have a cusp maximum happening at the origin 0, 0. Right at the critical number of x equals 2, we have the trend change from decreasing to increasing, so x equals 2 will be a relative minimum. It will be a normal relative minimum because x equals 2 came from the numerator. It has an x-coordinate of 2 and a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of 2, which will be 2 times 2 to the 2/3 power times 2 minus 5, which is 2 times 2 to the 2/3 power, and then 2 minus 5 is a -3. We can bring the -3 out front with the 2. 2 times -3 is -6. And then 2 to the 2/3 power. 2 is not a perfect cube. We can square the 2, and 2 squared is a 4, and write that as the cube root of 4 times the -6 if we wish, but it will not be an integer. So I'll leave it as -6 times 2 to the 2/3 power. For part I, we want to determine the intervals of concavity and any inflection points. All of this involves the second derivative, f double prime of x. Taking this directly from the first derivative, f prime of x, the first term is power rule. Bring the power down, multiply with the 10/3. 10/3 times 2/3, multiplying the numerators 10 times 2 is 20. Multiplying the denominators 3 times 3 is 9. X raised to, subtract 1 from the exponent, 2/3 minus 1, 2/3 minus 3/3. 2 minus 3, -1/3 power. For the second term, also a power rule, bring down the power. Multiply with the -20/3. Multiplying the numerators, -20 times -1 will be +20. Multiplying the denominators, 3 times 3 is 9. X raised to, subtract 1 from the exponent, -1/3 minus 1, -1/3 minus 3/3. -1 minus 3 is -4/3 power. We want to fully factor the second derivative. There is a common factor in the numerator of a 20, and in the denominator of a 9, and then we can factor out the lower of the two powers. That will be -4/3. It is lower by being more negative. Factoring this out, the 20 in the numerator will leave a 1 for each term. The 9 in the denominator cancels it out after being factored. And then factoring out the x to the -4/3. Factoring is division. Division is subtraction of exponents. By factoring out an x to the -4/3, we will be subtracting a -4/3 or adding a 4/3 to each of the powers. -1/3 plus 4/3 is 3/3 or 1. So it'll be 1x to the 1. Adding 4/3 to the -4/3 will be a 0, and x to the 0 is a 1. So we have left 1x to the 1, or just x, plus 1. X plus 1. We need the second derivative to have all powers be positive, so we're going to move the x to the -4/3 to the denominator. The 20 will stay in the numerator, so will the x plus 1. In the denominator, we will have the 9, and the x to the negative 4/3 will move down to become x to the positive 4/3. So we have the second derivative written as a single fraction. All powers are positive. It's fully factored. We can set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. In the numerator, it's factored, so that'll give x equals -1. In the denominator, x to the 4/3 equals 0 tells us that x equals 0 because 0 to any non-zero positive power is 0. We'll check to see which of these are in the domain. The domain's all real numbers. X equals -1, x equals 0 are both real numbers. They're both in the domain. They are both a candidate number. We can now draw a domain line, a line representing the domain. It has no left end because it begins at -infinity. It has no right end because it ends at positive infinity. We can put all candidate numbers on here in order. -1 comes first, then 0. This splits the domain interval into 3 separate intervals. We can pick a test value in each of these intervals. The first interval, -infinity to -1, we can pick -10. The second interval, -1 to 0, there is no integer in there, but we can pick -1/2. And the third interval is 0 to positive infinity. We can pick +10. We can now test the concavity by plugging the test values into the second derivative. We only care whether it is positive or negative, and therefore we'll plug into the fully factored version, which is this one here. A couple things about this. In the denominator, we have x to the 4/3 power. That means the cubed root of x, which can be positive or negative, but then to the 4th power, because of the even power, it will always be positive. Multiply that with the 9 also in the denominator, and it will still be positive. So that denominator is always positive for every test value. In the numerator, the 20 is always positive. And so the only part that will determine the sign of positive or negative in the second derivative is the x plus 1. So we can plug everything into just the x plus 1. Plugging in the -10. -10 plus 1 is a negative. We have a negative second derivative. This corresponds to concave down. Plugging the -1/2 into the portion of the second derivative that matters, -1/2 plus 1 is a positive. We have a positive second derivative. This corresponds to concave up. Plugging the test value of 10 in to the portion of the second derivative that matters, 10 plus 1 is positive. We have a positive second derivative. This corresponds to concave up. Right at the candidate number of x equals -1, we have the concavity changing from concave down to concave up. So x equals -1 will be an inflection point. It has an x-coordinate of -1 and a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. Y equals f of -1. It's best to plug into the factored version, so this will be 2 times -1 to the 2/3 power, and then times -1 minus 5. So this will be 2 times -1 to the 2/3. That means the cubed root of -1, which is -1, and then squared. And then we have a -1 minus 5, which is a -6, which is 2 times -1 squared is +1, and then times -6. 2 times 1 is 2, times -6 is -12. And we have a corresponding y-coordinate of -12. Right at the candidate number of x equals 0, we have the concavity not changing. It's concave up, and then it's concave up again. And that's because we found x equals 0 back in the first derivative and trend to be a cusp maximum, and that means it will appear as a candidate number and have a concavity not changing. So no surprise that that happened here, but because the concavity didn't change, it's not an inflection point. So -1, -12 will be the only inflection point. We can now graph the function. We have a vertical axis. We have a horizontal axis. We have a domain of all real numbers, so it'll cover the entire range of x values. We have no symmetry. We have a y-intercept of the origin. We can label that. We have x-intercepts of the origin as well as 5, 0. If you have a y-intercept of the origin, you always have one of your x-intercepts to also be the origin because it's technically crossing both axes. But we have a second one happening at 5, 0. That's over here somewhere. We can label this one. We have no vertical asymptotes, no holes. We have left end behavior of negative infinity. That means over at the left end, it's going to be down here in the negative infinity. It'll go down there somewhere. And right end behavior of positive infinity. So on the right end, it's going to end up in the positive infinity up here somewhere. We'll be sure that it follows those conditions. Right at the origin 0, 0, we have a cusp maximum. So that means it'll be taking a cusp shape, which means it's a maximum, and it'll look something like that. Right at the point of 2, -6 times 2 to the 2/3. Now 2 to the 2/3 is somewhere around the cube root of 4 value, which would be about 1 point something, maybe 1.5 times that -6 will be about -9-ish or so. So 2, something about -9. It'll be down here a ways, and that's going to be a relative minimum of some sort. So it'll have a shape of a relative minimum, like so. It's a normal relative minimum, not a cusp. We can label that. It will be x coordinate of 2 and then a y coordinate of -6 times 2 to the 2/3 power. And then right at the point of -1, -12, we have an inflection point. -1, -12 will be down here somewhere. We can label that as -1, -12. And that's going to be inflecting. It's supposed to be concave down to the left of it. So something like so. Concave down means it's curving down. And then it's going to be concave up to the right of it, so like so. But it's not supposed to be a plateau, so it's not going to go horizontal there. It'll sort of cross through the point in a diagonal fashion, like so. And then from there we can connect this together with there, finish it out here. Connect these together here. It's supposed to be concave up for the entire portion over here. So it's going to cross through like so. And there, it follows all the properties. It is meeting the left-end behavior of negative infinity and right-end behavior of positive infinity as it should. So this will represent our graph of f of x.